Ja, så er klokken 11, og rigtig meget velkommen til det tredje webinar i webinarserien dette, printe og store emner. I dag, hvor vi skal kigge nærmere på WAAM, som er Wire plus Arc Additive Manufacturing, eller simpelthen svejsning med tråd og robot. Så vi har nogle deltagere fra MX3D i dag, så fordi de ikke kan dansk, så fortsætter jeg nu videre på engelsk. So yeah, this is the third webinar. It's the WAAM. Here we'll have the speaker Thomas Van Glabeke from MX3D and our own in-house specialist on quality assurance of additive manufactured parts, Johan Braüner Nielsen. And again, the possibility of gathering so many companies into this webinar series is through our AM-Link network, which is a problem-solving hub for anything additive manufacturing related, if it's from plastic, polymers, concrete, composites, metal, whatever the problem, we have a network where everybody is specialized within something, creating a super hub of competent and specialists within anything additive manufacturing related. It doesn't matter where you are in the progress, if you are just on the idea, if you have the design, or if you are in production or decommissioning, AM-Link can help you in any aspect of the project. We do have a LinkedIn showcase page that I recommend to follow. Here we post customer cases, make introduction of new partners, but also announce webinars and other relevant content for additive manufacturing. So definitely recommend going into LinkedIn and search for AM-Link and press that follow button. So I think I can go straight to introducing Thomas. Thomas is from MX3D, which is a company in Netherlands who have made a slicer software for WAAM printing. They've made some cool things. I think a lot of you already know them from before, but I'll let Thomas do the speaking and the rest of the introduction on MX3D.
Thank you, Ivar. Let me share the presentation. Is that all displaying correctly?
Yes.
All right, let's kick it off. Like Ivar said, my name is Thomas Van Glabeke, and today I'm going to talk a bit about the wire arc additive manufacturing process. This will be the contents of the webinar. So first I will talk a bit about MX3D, then we will look into the WAAM history, where the technology is currently at, some of the materials that can be used, the advantages of the process, and then we'll really go into some use cases. And I will end the webinar with a digital hands-on session where we will go digitally through the WAAM manufacturing of a part. So first things first, this is me on the slide on the right-hand side. Thomas Van Glabeke, I am holding one of our 3D printing bicycles. I am an industrial design engineer, and at MX3D I focus on R&D. So MX3D. MX3D was founded in 2014 in Amsterdam, the Netherlands. And it actually started from a desire to make large-scale metal printing accessible, more flexible, faster, and cheaper. And together with the launch of MX3D, the moonshot idea of printing a pedestrian bridge was also created. The bridge by now is printed. It weighs over 6,000 kilograms and has a span of 12 meters. And by now, MX3D has printed over 20,000 kilograms of metal objects. We currently have 9 robots running, and we are a small team of about 15 people. MX3D is available for R&D, consulting, and production work. And since the last 2 years, we have also built a WAAM dedicated software, which we provide to the industry so they can get started with large-scale metal additive themselves. So let's dive into the history of wire arc. So the process we're using is called wire arc additive manufacturing. It is also referred to as DED arc, which is direct energy deposition through arc welding. And in simpler terms, it's just large-scale metal printing. So if we jump back 100 years, around 1920s, in the 1920s, the first patent for the creation of a metal ornament was filed. In the 30s and 40s, the currently widely known processes like TIG and MIG welding were developed. From the 50s to the 70s, arc welding was finding its first application for cladding and repair of parts. Then in the 80s, robotic arc welding is tested for the manufacturing of pressure vessels. And then about in the 90s, Rolls-Royce funds Cranfield University to really start looking at the potential for wire arc for the aerospace industry. By the 2000s, robotic arc welding accounts for 20% of industrial robot applications. In 2014, MX3D launched the idea, the Moonshot project for printing a 6,000 kilogram heavy object, and in 2016, the bridge was completed. And more recently, in 2019, our friends from Norx Titanium started supplying certified Tier 2 brackets to the aerospace industry. So that, in a nutshell, is where we were 100 years ago and where we are right now with the wire arc additive manufacturing. Let's have a look at the typical wire arc setup. Obviously, we are going to be using a robot and a welding machine. So first things first, we have the industrial robot. In most use cases, we are using a 6-axis industrial robot. This means 6 motors or 6 joints that can be moved, which allows us to orient the weld torch in many different ways. For the metal printing process, the most ideal orientation of the weld torch is top down, so vertical. And this will allow us to print with the greatest speed. Also displayed on the picture below the industrial robot is a manipulator. This can hold the metal object and rotate it while printing. And this gives us greater freedom in orientation. So we can rotate the part sideways so the weld torch can still be oriented vertically. Together with the robot, we are of course using a welding machine. And since we're basically welding non-stop, we are using the more beefier versions of these. And together with the welding machine, we have the wire feeder. In this case, it's mounted on the top of the robot. So these are basically motors that pull the welding wire either from a welding spool or a wire bucket through the liner and then pushes it along the robot arm to the weld torch. Then it touches the object, and basically we will build geometries by stacking welds on top of each other. So we're stacking welds in 3D space. Like I said before, we're using welding wire. So this is one of the consumables, and the other two are of course electricity to power the robot and the welding machine, and shielding gas. Depending on your alloy, you will use a different gas to cover the weld. In this case, the shielding gas is in a cylinder and mounted on the back of the welding device. To prepare the WAAM-print and to monitor it, there's a controller in place with the system. And to have consistent results and good logging, we also recommend a logging system. This could be on the same device. So this is a typical WAAM setup. Let's take a look at some of the materials. In theory, we are free to choose any weldable alloy that exists on the market. And MX3D has had good results with a wide variety of materials displayed here, such as stainless steels, carbon steels, high-strength steels, aluminum, and bronze. But the user is free to choose whatever he or she wants to weld with. The printing speed or the deposition rate depends on the characteristics of the alloy, such as the maximum interpass temperature, and of course, the shape of the geometry. If you're printing something thin, it will need a lot of cool down, so the printing speed will be lower, but if you're printing a solid block of metal, the print speed will be high. On the right-hand side, I've put 3 pictures of printed stainless steel, bronze, and aluminum. And on the bottom, you can see how it has a distinct weld bead shape. And on the top, it is post-processed because wire arc additive manufactured objects can be post-processed just like any other metal object. So in this case, the wire arc is a near net shape process. And if we want to have high precision, we can post-process like on the top, and we can achieve accuracy. Like I said before, we're using a computer to prepare the process and to control the process. In our case, we are using Metal XL, which is MX3D's own developed software platform, and you will see this in action a bit later in the webinar. Now let's take a look at some of the advantages of wire arc additive manufacturing. The first column is the reduced lead time. Since we're using wire arc, we are having a very high deposition rate. It's one of the fastest metal printing processes. And it, of course, comes, like I said before, with the near net properties. Printing deposition rate varies between 1 to 7 kilograms per hour. And that means that that we can fabricate metal shapes very quickly, and if precision is required, we can only mill those features that are necessary. But if structural reasons or structural calculations require it, we can also mill the complete part so that we remove anything that has the bead type look. It's of course a digital manufacturing process since we're using computers to steer the process, and manufacturing can be done on location. So wherever you drop your WAAM setup, that's where you can manufacture the parts. The second pillar, agile production. The whole flow is computer controlled, so we have a lot of computation power available. And since we're using a 6-axis arm and maybe a manipulator, we have a lot of geometric freedom. Since it's computer controlled, we can also customize the parts. So the robot does not care if the part that is being printed is the same every time or if it's different every time. This means that mass customization has the same price as mass production, which is very interesting. And since we have the geometric freedom and the customization possibilities, we can optimize the parts further than that is possible for other manufacturing techniques. Basically, the WAAM process or the WAAM manufacturing method is a digital foundry. The last column, reduction in total cost. We're using a standard industrial robot standard welding machine, so we're using off-the-shelf equipment. Companies are free to choose their own robot brand or their own weld machine for this process. And if they already have welding robots or a weld robot line in their factory, they are just a software license away of getting started with large-scale metal printing. Since we're using these robots, it's of course highly automated, the process. And since we only print what we need, or at least near net shape, we have very little waste. If we're looking at CNC milling, we're always milling back from a block to the shape. So we have a lot of waste, but in case of 3D printing, or in this specific case, wire arc, we are building from nothing the material that we need. So a lot of waste reduction. And the final advantage is, of course, the digital stock. We do not need to have warehouses laying full of parts, since parts can be printed on demand and can be kept digitally as a stock. So just on your hard drive, and you print them when you need. Now we're going to take a look at some of the use cases, some infrastructure construction parts, heavy industries, oil and gas, and also a design object. So first and foremost, the MX3D bridge. This is maybe the project that you know MX3D from. Like said earlier in the presentation, this idea was conceived in 2014. And it took about 6 months of printing with 4 robots to fabricate the final shape of 6,000 kilograms and 12 meters long. So the bridge was fully additive manufactured. It was designed by one of the founders of MX3D, Joris Laman. And one of the key aspects of the bridge design is that it's based also on the structural calculations, which you see on the right-hand side, the drawings. There you see the red and blue stress and compression lines, and you can see how these were translated to the object. So where we have a lot of force, so in the red zone, the bridge clearly has thicker sections, like in the handrail. And if we look at the top, we see that the forces are also being carried by the grid frame of the bridge deck. Also, where less forces come into play, the bridge has a more perforated or open structure. So for this project, we can see how wire arc can be used for rapid manufacturing of large parts. We of course exploit the free form of shape. Making this shape with any other technology would be very complex. And of course, we allow for optimized designs, as seen in the structural drawings. Second example is the Arc Bike 2. The idea behind this showcase is to show really the raw speed of the WAAM process. The first day, the rider can give in his or her biometric data, and an algorithm will design the bicycle frame to his or her dimensions. It will also design the frame within manufacturing specifications so that it becomes printable. The second day, the frame is printed because the frame has a print time of about 24 hours or less. And the third day, the frame can be assembled with the hardware components and can be ridden home. So with the Arc Bike 2, we really wanted to show how you can go from design to final object in a matter of days. So here you can see how wire arc can be used for either rapid prototyping or rapid manufacturing. And it can be made very efficient using optimization algorithms. Showcase is the MX3D robot arm. Wire arc is often used as a manufacturing method to repair or replace broken parts. And sometimes the original model is not available anymore, like with the case of our palletizer robot. This is an old robot that we took apart and we replaced the lower arm. The initial model weighed, the lower arm displayed in orange, weighs 145 kilograms. And together with Altair, a leader in simulation software, we were able to trim the weight back down to 71 kilograms, which is a reduction of over 50%. And then with minimal post-processing, we installed back into the robot. The printing time consecutive was about 4 printing days and then minimal processing. So that's very fast for a large-scale metal part. So with this use case, we wanted to show that legacy parts can be replaced in a short time with a new and better alternative. And you can imagine the possibilities we get when we lightweight one part with 50%. For example, the electricity consumption of this robot will be reduced, or we can put in motors with less torque, or the robot specifications will just be better because the robot could lift heavier payloads. Next example is more of a simple wire arc additive manufactured part. This is a connector flange, and it's for the oil and gas industry. In the oil and gas industry, there are many standard components, but sometimes unexpected situations demand urgent repairs, resulting in custom components. Also, sometimes these parts are in very remote locations, and production there or even shipping there could be already quite a hassle. With wire arc, you can print locally and manufacture locally, so you do not have that long lead time. In this specific use case, we have printed a connector flange, and the printed weight is 18 kilograms. And with minimal post-processing, we have an end weight of 16 kilograms. The print time in total was 16 hours, so about 2 normal working days. And this is very hard to beat if you look at the lead time of casted parts. This is an example for the construction industry where we have manufactured a large-scale metal node. These nodes serve purpose in complex roof structures or paneled structures of buildings. And these are often designed symmetric so that they can be easily manufactured by welders. So usually these are manually assembled. With wire arc, we have a lot more freedom in complexity of the shape, and every node can be different. So this means that the architects have a greater design freedom, and we can still have a consistent output in production. The node project was a collaboration with the Japanese construction company Takanaka, and we researched much more than just printing this node, as you can see from the pictures on the right. But this could be a webinar on its own, so I will leave this slide as it is. Now, as a final showcase, we're looking at another maritime component similar to the oil and gas. But the difference here is that it is a simple design, but it is made by skilled workers because it's made from many different parts of bent sheet metal. The advantage of using wire arc here is that it's of course computer controlled and it can be carried out 24/7. So instead of having 3 skilled craftsmen build parts, we can have 1 craftsman or robot operator monitor 3 robots instead. And as you know, the robot does not need sleep. It does not know holidays if maintained correctly. So the output can be a lot higher. So now to go to the final part of the webinar, we're going to have a little hands-on digital wire arc session. We're going to take a look at a very popular use case of the process, which is printing blades for a propeller, so maritime industry. Currently, these are often casted and then post-processed with grinding to get them ready for installation. And producing propellers with wire arc is actually very similar. As instead of casting, we're doing wire arc, and the post-processing takes a similar time. The 4 steps we are going to take a look at is the print preparation. This will be done with MX3D Metal XL. Print monitoring. This is MX3D Metal Live. We're going to look at the print carried out by Force Technologies. And then we will finalize the webinar by taking a quick look at what you can expect from the logging with MX3D Metal Viz. First, I will give you a typical overview of how to tackle a WAAM project. So usually we start with a design file. This can be an STL shape of your desired printing geometry. And based on the shape, you will choose a desired material or welding alloy. So first things that can be done is to qualify the material by printing some standard geometries. And here from this, we can deduce slicing parameters. Then we will analyze the object for print feasibility, and we will generate the toolpaths. So the slices of the object will be transformed to toolpaths for the robots and welding instructions for the weld machine. Then we will carry out the printing, and the printing will of course be monitored by the computer in order to achieve process control. Then afterwards we will take a look at the log. And as you can see from the picture, every step along the process is going to be logged to make sure that everything is within the right parameters, and we can prove that different runs of the same object will run in a repeatable fashion, because this is very important if we start to look at the certification of 3D printed parts. So first things first, MX3D Metal XL. Let's see. So we start with selecting our robot. This can be KUKA or ABB robot or another brand. We name our project, and then we import our CAD file. Here we can position it in 3D space where we want it compared to the robot, and we can take a look at print feasibility. In this case, the shape is very straight up, so everything is very printable. We're selecting our alloy. This can be an MX3D library alloy or your own. In this case, we are slicing with a layer height of 1.2 millimeters. Now we are slicing the geometry, so we're generating toolpaths. And this is the result of those. So here we can see how the robot will build up the shape layer by layer. The yellow arrows indicate the printing direction. So you can see that we're continuously going from left to right and then from right to left. We also see the print statistics, such as the weight, gas consumption, required wire, and so on. And then we can solve it. And this means that we calculate the motion paths for the specific robot that we have selected, and we solve it so that it can run without any problems. Then we click on the live button, and the file is being sent to the robot, and we're ready to press play. So next thing I want to show a time lapse that Force Technologies has sent us to show how the print is carried out. Let's do it like this. So this is a sped up version, of course, but here you can see how the robot goes left to right and builds up the propeller blade weld by weld. And while this is going on in practice, we can look at the digital equivalent through MetaLive. And with MetaLive, we can see what the robot is actually doing, what position it's at, what the current deposition rate is, what time has passed, what will come. We can also see the live welding variables such as current and voltage and stick out. So this is a very handy tool for the robot operator to ensure that the print process is going like it should. So after the print, we are going to take a look at the final step, and that's the logging and the log process. And this is basically a point cloud of a lot of process data. We are now taking a look at MX3D WeldVis, and here we can see every measurement in 3D space. So in this case, we're looking at the current of the simulated print, and we can see that it's distributed very evenly. Like said before, the logs will serve as a handy tool for the certification of your parts, and of course showcasing that the print process was carried out consistently. This is the final slide of my presentation, and I would like to hand it now over to Johan, who is going to talk a bit more about the actual testing of wire arc parts. Thanks.
Yeah, perfect, Thomas. Very good presentation. Thank you very much. You can also see we got a question here from Trolls. I think most of those questions are going to be answered in Johan's presentation regarding anisotropy versus isotropic and post-processing needed. It's going to be covered in the next part of the presentation. Share the screen.
Yeah, feel free to put any questions in the chat box, and if they don't get answered now, I can also get back to you after the webinar.
Yeah, we'll do a summary after Johan's, where anybody can write in the chat or unmute themselves and ask some tricky questions. So
I have control now.
Yes.
Yes. Well, thank you for the presentation, Thomas, and the introduction, Ivar. I'm gonna try to make it. It's gonna be very short, very brief, because actually testing of materials is, it gets quite technical. But I'll try to give a short introduction on what is quality and how do we assess it, and what are some of the considerations we need to take into account and think about when we are dealing with something like additive manufacturing. If it is, yeah, okay, there we go. So as I said, material quality, quality assurance, quality control, and a short summary to sum up what we talked about. So material quality, what is that? Essentially, it is the sum of the mechanical, chemical, electrical, and thermal properties of our material. In this case, it would be a metal. What the exact focus is will depend on the specification by standards, along with those of the manufacturer, as well as the buyer or whoever is designing a part or building or whatever with these components. Where additive manufacturing spices up the traditional testing is that we no longer just have like these cast and wrought materials, but we also have different manufacturing techniques like laser cladding or selective laser melting, which is the powder bed methods, and then we have wire arc additive manufacturing, as we're talking about today. Each of these will have different sensibility to control of the process parameters, and will use different microstructures on some level, and have different native vulnerabilities perhaps, and that will lead to different properties and different challenges, depending on if they're done right or not. So if we test the mechanical properties, which we want to do because often we have these components that are designed for a mechanical load, and we can actually do this by normal standard testing, such as tensile and hardness testing. That is fully possible, and we can do that on the individual like small test samples designed for the purpose, or we could do it on full parts depending on the geometry of the parts and depending on the complexity of it. If we are talking about very complex parts, it is a good idea to also include modeling. We saw some of that in Thomas' slides as well, where we see how the load is modeled and simulated, so we can identify perhaps critical points and critical sections, and then design tests to load these and test them specifically, and thus basically minimizing the amount of tests that we need to conduct. So as an example, I will throughout the presentation have like few examples from early constructed for the purpose of illustrating these things, and from early development projects. Here we have WAAM manufactured 308 and 2205. That is both stainless steels. 308 is an austenitic, and 2205 is a so-called duplex steel. They both perform well, but we can also see that here in the comparison with the conventional material, both of them seem to perform subpar. However, I've taken this to illustrate a point that when you are comparing to conventional manufactured materials, you need to remember that you also have different qualities in the conventional materials, and what is right to compare it with. That both comes into play the standardization work, but also what are the conditions, what are the loads, the environment. So you need to look at your specific application as well. So overall, actually, we have good mechanical properties here. And yeah, Ivar was also mentioning it a little bit with one of the questions, that they are anisotropic, which means that we have different like variation in properties depending on the direction compared to the print direction. Which essentially comes to this, that we are now building up. So we have like perhaps we have the wires, the printing going along this plane and also along that plane, and all in all, this combination of heat input and cooling and heat and cooling will yield differences in the microstructure, and the microstructure is essentially what governs our mechanical properties on the material level, whereas for the parts, it's the design as well. So of course, when we print something, we want to control that it's okay, and because we don't start out with this big mixed pool of molten metal, so we get this more layered structure, as we can see here by the indication of lighter and darker bands. And with this being a duplex steel, it's important to also control that we have the right amount of different phases in the steel. And yeah, here's the ferrite content controlled, and actually both the dark and the lighter areas are within specs for 2205. And then of course we will also look at irregularities, or are there intermetallic phases that might be more critical in something like aluminum, where some intermetallic phases can cause corrosion to the aluminum matrix. And in this particular case, we saw some some secondary austenite, although not critical. It's just not something you would see to the same degree in conventional material. Because we also often want to do these complex geometries and use minimum material, we have here made a wireframe structure, and this is actually photographed with X-ray, meaning that we are looking at differences in the material thickness without destroying the material, and we can see like some indications that we have maybe less material here in this section, where in the idealized design this could be identified as a critical point, and maybe it's even more critical now because we have appearance of a small crevice, and for the sake of illustration we then cut it up, and as you can see here from this metallographic cross section, we do indeed have a crevice, which can both be critical from a mechanical standpoint but also from corrosion. So when we talk about corrosion, then yeah, corrosion of 3D printed metals is happening by the same mechanics that you will have with normal steels. The only difference is that you may have more inhomogeneous structure, which can, depending on your control of your print parameters and the quality of your product, can be more or less. And then we have this thing where the heating and cooling will impose some stresses into the material, and whether that's a problem or not, that's again something you need to look at. And then finally, when you talk about stainless steels, for example, then you have a passive surface film that protects the steel, and you also want to look at that quality, which is actually something you do with normal stainless steel as well. You also check that you have a sufficient surface film formed at the foundries. So essentially, when it comes to corrosion of 3D printed metals, the challenge is actually just to produce representative test samples, because we have this freedom of geometries, and so we have like maybe some things that affect the microstructure or impose different stresses. So how do we do it then? Well, as I said before, we need to think about the application. We need to think about, is it possible to do surface treatment after printing? Because there tend to be a difference in as printed compared to a machine surface. But we have a wide range of possible tests. These are just examples, and actually all of these are taken, like they're used for conventional materials as well. And if we take something like the electrochemical, it gives good quantitative data, but it's hard to do on something as printed, because the surface texture has extremely large influence on the results you're getting, and therefore also something like the specific pitting corrosion test with the electrochemical cell is difficult. But then you can use something like a G48 pitting test or one of the other immersion tests, or you can use climatic chambers like humidity chamber or neutral salt spray testing, which is both commonly used in both the verification of normal stainless steel and for various offshore purposes. Yeah, so a short example is, for example, we want to check that our product has the ability to passivate on the surface and doesn't have like small defects in this passive film. It's like you have a raincoat, but there's small holes in it along the seam. Then you'll start getting wet from there, and eventually you will be wet all over. It's a similar, it's an analogy at least of sorts. So the idea of this copper sulfate test is that if you have free iron or free iron oxide or iron oxide, which is not able to passivate and protect the steel, you will get copper deposition, which is what we see here. When looking at the before, we have some dark areas, which I would naturally suspect to be some oxides left over from printing, or it can also depend on your cleaning process if you remove these or not. But we see that we get this slight copper coloring on a lot of these parts, which indicates that we here don't have the necessary protective oxide. And then to the question whether it's necessary or not, well, here we conducted some immersion tests where, yeah, we can see that some of the areas where before we saw some copper depositioning near these little droplets, and here we also see that corrosion has initiated here. That is also because the tests here are will naturally initiate in sites where you have a crevice or a small pit, and you will see exactly the same thing if you have a small pore in a weld when testing that. And testing welds with G48 is extremely common, and in a lot of ways you can say this is similar to a weld. And this last one is actually just to sort of show that it's also important to know what you're looking at, because here we have a duplex plate geometry printed and exposed to neutral salt spray for various numbers. It's the same panel carried out through all, and we see some corrosion in the beginning around 504 hours, and we see that it appears to have developed when we reach the 2600 hours. When you clean this panel, because you might be inclined to say, okay, this is not good enough. That's not true. When you clean this and when you look at it, there's actually no damage on the panel surface itself. What we have is a slight crevice forming under the protective paint along the edge, and then that runs with the corrosion products out on the surface, because we have a sort of a wavy geometry on this, although it is a plate. So to say it, like, summarize it very shortly, we do tend to see more inhomogeneous materials, but it doesn't mean we can't test it, and we can't use we can actually use conventional test methods to control this. We also have the ability to control the very complex geometries and check for small errors there if by using X-ray without destroying the component. And if we keep in mind the importance of surface defects, we also know whether or not it's necessary to machine a part. Also, of course, depends on the design specifications, but you can also use a material in different conditions, whether it's machined or not. And the key point is actually just to, when you design your test program and when you design which parameters you want to specify when purchasing or printing parts, well, keep in mind what is the use for this specific part and where are you going to use it. We saw from MX3D that we have parts used in traditionally and still very corrosive environments. So it is indeed possible. I, of course, from my perspective, have to have a very critical eye to it, but it is indeed possible, and we see WAAM manufactured parts applied in aerospace, which is, an area where you have extremely high standards for quality control and assurance. So the final point is that standardization work is actually still ongoing. There are various groups, both within the ASTM and the ISO, that are dealing with WAAM manufacturing and other manufacturing methods. So it is still, for that part, it's still a work in progress, but it doesn't mean that you can't control it and you can't test it, and you will know if you have a good product or not. So, and that would, that would actually be it.
Yeah. Perfect, Johan. Thank you for a very thorough introduction on the quality assurance. And the quality assurance is very critical for me and Thomas, who use the software, who use the method, because when we're trying new materials, it's not just plug and play. We print a lot of different test walls that we can send to Johan and his team, and they can tell us which parameters give the best result with a minimal amount of defects or what it is. If we aim for Truls Sturm's question, I think he was answered on the anistrophy of the part. Yes, it's going to be stronger in some direction, but it's not far off. It's not like there's miles apart in the tensile strength. So also when we test materials, we print the dog bone for the tensile test in different orientation to see which one which values are we getting for each direction. Post-processing isn't necessarily needed. It all depends. If you post-process and grind the surface of it, you're going to see a much less corrosion attack on the surface as compared to leaving it as printed. But I mean, there are possibilities to paint it, coat it. So there are definitely workarounds. So it all depends on what you need for your part and the environment that it's going to be. So, and you also ask if there's going to be support grid like in polymer. Technically not at the moment. It's more just printed solid. But I don't know if Thomas, you are in the R&D. Is that something you're working on to have more going from maybe a 25% infill?
We're trying to avoid support because since it's metal, it doesn't snap off like plastic printing. So anything that needs to be grinded afterwards, we try to avoid as much as possible. There are cases where we want to have a larger footprint. Let's say we expect warping or a lot of heat input, then we do want to increase the footprint and then we might have more support. In terms of support removal, sawing is a valid option, plasma cutting and grinding. So it is possible to have infill support, but usually if we use it, it's either 100% or it's a branching structure. So it ends up being, it starts with the spread, like 30% infill, and then slowly it grows to 100%, and then the shape is built on top. So that is also a viable strategy.
Yeah, thank you. Are there any other questions? People are. Let's see, David is asking, was it difficult to get the propeller certified for sea trials?
So in this case, I think Ivar ran this propeller print. MX3D has also printed propeller blades in the past, and there are other companies who had different levels of success with certifying propellers. So it is possible, but like Johan said, the legislation and the ruling for the certification of wire arc is not fully finished. So we're definitely checking all the boxes that we can, but quite soon we expect to have a complete coverage of guidance notes, and then this will become more accessible or faster accessible. Yeah.
Yeah, that's a very good point. I mean, we are seeing space applications and aerospace application all getting certified. It may not be the traditional route of just following a standard, but it is definitely possible to validate it and certify it for the different industries. But they are trying to make it more streamlined so that everybody can perform. Can you elaborate on cost? Truls asks.
So in terms of the setup that MX2D is using, a standard industrial robot and a standard welding machine, these costs are of course free for you to spend on whatever brand that you want. 6-axis industrial robot, just ballpark figures, depending if you can get one second hand, it can be as low as 12 to 15K. Newer ones start 25, 35K, and this is for a robot with a height of about 1.5 meters. This is the robot model where we at MX2D have at least 7 or 8 of. So a robot price maybe around 30K, welding machine between 5 and 15K. Then in terms of operational costs, of course you want to write off the robot and the welding machine. But if we're talking about the other things, welding wire, very cheap. Normal steel, €2 per kilogram. So compared to other metal printing processes, wire arc is very cheap in terms of consumables. Electricity, it's the same as with standard welding. Shielding gas, also fairly cheap. So yeah, depending on how fast you want to write off your robot and your welding machine, operation hours maybe around 100 euros or maybe 50 euros. I mean, it all depends, of course, on what type of setup you wanna start with to write off, but operational costs are very low.
Yeah, for a good answer. And in Aimlink, we have both robot suppliers, shielding gas suppliers, wire suppliers. We also have this in our facility in Linne. If it's something that you want to try to see, is this something that we can benefit in our production? And then our machine is also available, and guidance from Thomas is also possible. So if you have any parts that you are considering for WAAM-print, please contact me, and I'll set up a meeting with the relevant partners afterwards, and then we can look if that is something that has a good business case for your business.
Maybe to elaborate a bit more on the cost, so MXUD is usually going for the industrial robot welding machine approach. There are other providers that provide box solutions, so that's more like acquiring a CNC machine where they just drop a box in your production hall, and these start from quite a bit higher price point, I would say 250 to 300,000 and up. This is also something MXUD can provide you, so feel free to get in touch if you want to crunch some numbers.
David asking, is there a lot of maintenance downtime for WAAM? No.
So in terms of maintenance, we are just doing robot maintenance and welding machine maintenance. Of course, the consumables like welding tip, liner, and so on, those have to be replaced, but in general, downtime is very, very low. In terms, in comparison to printing time, I'm not sure what the numbers would be, but downtime is like 5% or something. I don't know, but it's very low. The robot is most of the time it's just printing.
Yeah, and I agree. We have experienced very low downtime. I mean, you can pause the print in the middle of it, change your tip, and then continue. So it's very fast.
So for maintenance of the weld torch, tip, and gas shield, there's also automated solutions available where the robot goes to a tool station and everything gets cleaned and calibrated in a matter of seconds. So downtime is, it's not really a big work in progress or anything. It is very smooth already.
I think I can ask more reflective question to you, Thomas. I mean, you are working in R&D and developing a lot of things and new methods and new approaches. I can see in your background you have the dot welding. Could you explain a little bit more about the dot welding and what's in the future for MX3D?
So the dot welding, well, actually, I have a part here behind me that's dot welded. So here we call it dot printing at MX3D. It's the same as spot welding, but instead of placing one spot or one dot, we're just dotting on top of each other. That allows us to create very free-form grid structures in 3D space, like this one. For MX3D, we've mainly used this for art projects. We've used this for benches, for bars. Sometimes we've used it for an industrial project because of the freeform that this strategy allows, but it has a very low deposition rate because we're placing one dot only instead of continuous lines. So it is interesting. Industrial relevancy is a bit lower. It's morely like a R&D technique. And I think your question, Ivor, was a two-part. Well, what was the second part?
Yeah, where do you see the technology, the WAAM technology, developing over the next years?
Yeah. Well, like we touched upon, certification is being developed very intensively. For MX3D, we want to provide all the tools required for our clients to get their parts certified, because this is really the next big thing. So this is what we're going to develop heavily towards. I think in the coming years, we will see more and more certified parts in a wider range of industries. Obviously now aerospace, that's where it's starting. That's where a lot of money is to be gained. And of course, there's more research money available to do this type of things. But I think we will slowly see it spread wider to, for example, the heavy industries, you know, parts that have wear and tear, cladding operation that will be more than cladding, will be really 3D printing, repair of parts. We're seeing other companies and also ourselves printing some lower tier parts or like lower parts that don't have critical use. So more like yeah, you know, caps and protection items. And I think there we will slowly gain more technological advances, and we'll start printing more and more critical parts there with the technology as well as we get certified along the way.
Yeah, perfect. Thank you. Looking forward. Yeah, David has another question. This keeps coming. It's good. How hard is it for maritime CAD engineers to learn generative design? I think I can answer that one. So my background is from wind turbine CAD design and engineering. And yeah, it's very, very traditional, but you're working with the moleskin, you're working with the frames. And then, but from my personal experience, it wasn't hard to go from traditional design approach to learn the generative design. There are a lot of good tutorials. We also have a lot of good specialists within Aimlink that can help. We can set up a possibility to set up workshops for your company, where you can get a more hands-on direct approach on how to change your approach, because that is very, very important for additive manufacturing, is to get that approach. So are there any other questions? We're about to run out of the time. Nope, doesn't seem like it. Rich, we'd just like to introduce the next webinar. The speaker is Dirk Roth from DMG Mori. He's going to speak a little bit about hybrid machines or direct energy deposition with powder. It's a little bit what Thomas says. That's one of those companies that they make a machine, they drop it off on your shop floor, and then everything is fairly plug and play, you could say. So looking forward to that. I will also follow up, because on our machine on Lindner, we also have the powder system. So we will speak a little bit about their system and our system, and how they are different and similar in use and user cases. So yes. And again, I did write my email in the chat, but if anybody wants to give me a call, send me an email. If you want to talk with Thomas more, if you have some parts, please reach out. Well, we would love to look closer if WAAM is a technology that you can benefit from. And yeah, if there's no further questions, then hopefully I'll see you all next week for the fourth webinar. Yeah, you can also send Thomas also wrote his email here if you have some direct questions there. So again, thank you, Thomas, for a wonderful presentation. Thank you, Johan, for nice input. And thank everybody for listening, and see you next week.
Thank you. Bye-bye.